All right. Well, thank you, people, as always, for being here. I want to start with assignment number 1 because I have seen some questions about that, and that's okay. If it's confusing, well, sometimes confusing is good because you are reading and you're trying to understand what it is. So let me help you with this. The first part is more focused on theory. Actually, you don't have to use R, only probably for this one and this one, but basically the first questions are more about theory, right? About what we have discussed about related to what is a model, right? And let me explain you first how you can answer this if you want to use quarter, for example, right? Because probably that part's a little bit confusing. Let me just open RStudio. If I can get access to the bar right here. It is. Then I'm gonna open a new. This computer is not working very well, you know. For some reason, it's not showing. Yeah, it doesn't show that. I have to bring another computer. Cannot even keep on the file. Let's see what's going on here. Because of this. Now, so here I just go to the document. If I want to, if I had another template, the computer and give it the template. In here, for example, I do assignment spell, right? Saria is asking, when turning in assignment number 1, do we need to submit a document with our questions and answers as well as the R coding and output files? Yes. Yes, Saria, the answer is yes. I'm going to explain you how that works. Yes. Yes, you're right. The answer is yes. Everything should be together, right? So, and I think that has been a problem for many people. So, let me show you how it looks like, right? So I go and create an important document. I go to source because I don't like the visual part. Here, delete this. Right. And in here, I'm gonna just have the date. So it will give me the date. Right. So in here, of course, we are gonna delete all this information because we don't need it. It's a template provided by RStudio. And here I'm going to answer, for example, I can do this, call this first part. And then the second level of headers is going to be each question. So this is question 1 or exercise 1, right? And if you want to be even more tidy about it, you can go here and you can copy the actual question right here. You don't have to type prime rate and all these things right here. If you want to, you can do it for your records once you are studying later the material, if you want to revisit the material later. Right? So this could be the starting point where I can see where you are responding the first question, right? And then, of course, I'm asking you here. Let me come back here. So I'm asking you here, what kind of model is this? And I told you that you can read page 8 in Westphal and Henning, right? let's do it right now. Remember that I told you that there are models that are probabilistic, right? They have a distribution. These models assume that there is a distribution in nature for your parameters, right? There is a distribution in nature for the data that you're trying to understand. There are other type of models where you don't have a distribution for those parameters. There is not a distribution, it's fixed, right? It's in that sense, it's deterministic. Every single time you plug in values, you will get an output that's exactly the same. Those are deterministic models. Probabilistic models don't work like that. They work with random variables, right? So every time you generate data, you will get a different set of values. So, for example, in R, you just go to R. If I generate data, for example, let's imagine that it's the opposite way. Here. 100, 3 and 1. So look at what happens, right? And actually, let me generate only 20 observations. Let me check something here. I don't see any. I don't know why I said that. Okay, cool. So in here, what I'm doing is just generating data, right? I'm able to generate data with a function that you see all the time in my slides. That is called random normal. Why? Because we are using a random probability model, right? It produces data. Well, let me show you the values, right? So look at that. These are the values that it produces. Now, let me run the code again and see the values that you can get out of this. Let me just print out information and let's compare the numbers. Are they the same? No, right? They're totally different. Every time I run this function, which is actually a computational translation of the probability density function of the normal distribution, I get different values all the time because this is a random model, right? So now let's use the other model. The model is right here in the assignment. Can I copy this? Nah, I will have to type. I don't want to type. I'm very lazy. Well, it's fine. I thought I would be able to. Okay, let's create a model, right? So let's create this model right here. I'm going to call it just model 1. And we have prime, right? How it was? Oh, I should call it prime actually. 60 plus 5. So let's call it prime. Right. So it is 60 plus 5 by poverty. Right? And let's assign some constant values for that. Like for example, poverty. We need a value for poverty. Right? So let's create different values for poverty. I don't know, let's imagine that this is an index of poverty that goes from 0 to 100. So 100 is a very poor family, and something close to 0 would be somebody who is less, like far from poverty, if you can say that, right? So I do this, and then, look at that, I misspelled the word. These are the numbers that I get. Now, if I do it again, I will get exactly the same numbers. So what is happening here? Well, the model that I'm proposing in the question number 1 is not a random model. It's a deterministic model, right? It doesn't produce data randomly. Every time you add the same information to poverty, you will get exactly the same information, right? Those are the numbers that I get. Of course, you can change the numbers, but if you try different iterations, you will get exactly the same numbers, right? It produces data, but it's not random. It's just the same information, right?
What room is that?
So, what is the answer to this one? What kind of model is this one? Well, you can do, if you're using Quarto, if you're using Word, it's fine. You can just copy the question and put it there. But if you're using Quarto, you can just write in simple words, what kind of model this one? Well, this is a deterministic model. And that's the answer, right? Now, let's check question number 2. Is this model good for studying crime, right? And actually, I'm going to copy this and put it here. And if you want this to be bold, you can, I believe, you can do 1 asterisk like this. And this will become bold once you parse or once you render that PDF file. Is going to be bolded, right? Cool. So, after you have a question?
I actually think it's 2 asterisks.
Ah?
I think it's 2 asterisks for both.
Yes, you might be right. Yes, you might be right. I always forget the rules.
Yeah.
Let's see if it's 2. Because I started using markup languages with LaTeX, and I learned some other rules. But yeah, you might be right. Because I believe 3 asterisks is italics and bold.
Yeah.
I believe, yes. Yeah. So, is this model good to study crime? So, the model that I'm proposing in segment 1, what do you think? Is it a good model for that? Makes sense to have a deterministic model for crime? It's totally deterministic, right? Every time you run the model, you will get exactly the same information. That means that you have 0 error. A deterministic model has 0 error. There is no error in my prediction. Every time I estimate something, it's going to be 100% accurate. Is that something good for studying crime? No, right? Crime is something that happens for many factors. It's a multifactorial phenomenon, right? Crime is not like you can predict crime and exactly predict who's going to be a criminal. It doesn't work like that. There are many variables to take into account in the criminal behavior, like, I don't know, SES, level of education, and many things. And even if you have all the variables to predict crime, you still have error. That's why we prefer random models. Random models will assume that there is error all the time, right? Deterministic models will not. They only predict this is going to happen every single time if you add exactly the same information. There is no error, right? So, of course, what is the answer to this question? No. The answer is no. A deterministic model is not the best model for studying crime, right? And actually, leave it right down here. And of course, you can write more about it, right? I'm not going to write more because, of course, you will stare at me, stare at the screen, and I will be typing. That's kind of boring. Now, let's see the other question. I'm giving you just a hint, right? And the question actually is this one. Please write the name of 3 probability models that we study in class, right? This is 1.3. What do you think? Do you remember 3 probability models? It's actually the name of 3 guys. We have the studies on guys here. Yeah, tell me.
Purity,
Which one?
the purities, probably, purity statistic probability 1 and 2 and 3. I think 3 of them.
I couldn't hear you. So wait, what?
The purity statistic probability
Yes.
1, model 1, 2, 3. That's the 3 name.
Yes, but what is the name of those models?
Statistic probability.
No, it's not that. It's just the name of 3 people, actually.
Oh.
We haven't studied these ones,
The Bernoulli,
Yes,
the Poisson,
yes.
and then I didn't see the other one is a probability model, but
No, Gaussian.
is it Gaussian? Yeah,
Yes.
I was gonna say.
Yes, Gaussian, or you can also use the word normal distribution.
Oh, okay, yeah,
Yes,
Okay.
that's the answer to that question. Yes.
okay.
Exactly. It's just the last names of 3 people, right?
Uh-huh.
Those are the models that we have studied so far. Or some people Google this question. I have seen that many times. And you might find, actually, I Google my assignments because I repeat some questions, right? And there are websites where you can buy the answers. That's amazing. They are selling my property. That's nice. But the answers are wrong. That's kind of fun. I Google all the time, and the person who answered that is totally wrong, right? He wrote like a mambo jumbo explanation of many things, and I'm like, man, you didn't write the book that I'm using for my class. That's for sure, right? So, and the answers are wrong. So don't wait for that, actually. Yeah, you will find it there. If you copy and paste exactly the same question online, you will see some web pages selling the content, which is crazy. I didn't know that. I'm so excited about that. You know, I feel great. But yeah, they're wrong. I tried to get, and actually I got access to some of the answers, and yeah, they're totally wrong. And I can recognize when you copy and paste from there. Of course, I can do that. But yeah, those are the answers for that question. Or if you write probability models in Google, it will tell you a lot of names, right? And that would be correct. If you do that, if you mention the Cauchy distribution or any other distribution, that's a probability model. We haven't studied those ones here, but they are true, right? They are probability models. I'm not really asking you. Oh no, yeah, I said we studied class. Yeah, I didn't mention like any probability model. But yeah, even if you do it, sometimes they give you points. At least you were online and you went online and Googled it. Now, question number 3. It says, oh, actually that one is number 2. Let me just change the number here. Number 2. So I should change this to follow my convention. You don't have to follow the same order. You can create your own order, but this could work. So in here you would write Bernoulli, Gaussian, and Poisson. Right? Perfect. Now let's go to question number 3. Actually, when I use number 3 here, sometimes it gives me an error, like this hashtag here again, because it believes it's another heading. So I'm avoiding to use the number that this character here in order to avoid confusion for the software. Sometimes it works, sometimes it doesn't. So I don't actually add the hashtag there, or well, pound sign. It's a better way to say it. And so question number 3. It says that we're starting to. Okay, again, this one is not about R. Oh, in the first question that I was using R to explain this question. You don't have to use R, right? I was using R just to make my point a little bit clear, but you don't have to use R for that one, right? It's just words in the first question, right? Question number 3. What I'm asking is, let me save it first. Just save this. I'm going to render this later. So I'm going to call it. For some reason, it's not typing. That's amazing. Sorry about that. OIT updating my computer, but for some reason, it's not working like it should. Now it's working. Okay, cool. Homework number 1. That's how I'm gonna call my QMD file. Okay, so let's come back here. I'm asking you what type of information I'm assuming here, right? And everything's in the code. You don't have to copy this into your computer and generate a value. If you want to, you can do it, but you don't have to, right? So what am I assuming here? Well, I'm simulating data from what distribution is this one? Do you know? Normal distribution, right? Yes, it is a normal distribution. And actually, there are hints. You can see that I'm using the function rnorm to generate the data. So that means even if I don't include the plot, just by looking at the function, you might be thinking, he might be using the normal distribution because that's the function for the normal distribution power. So that's the first piece of information that you have for answering this question, right? The other is the values that I'm using for generating data. I'm assuming that this generated data has a distribution of always going to be closer to 50, right? A mean of 50 and a standard deviation of 20. So I'm assuming a mean of 20 and a standard deviation, mean of 50 and standard deviation of 20. And the distribution that is assumed is the normal distribution or Gaussian distribution. That's the answer. So when I'm talking about assumptions in simulated data, pay attention on how I write the parameters the values for the parameters. Remember that the mean and the standard deviation are parameters in my model. In real life, I don't know the values for those parameters. In real life, I don't know. That's why I collect data in order to be closer to those values. But in here, this is simulated. I can do whatever I want. I can specify any value to those parameters, right? So that's why when you see my code and I ask you what information is assumed, just pay attention to what I do in the simulation. That's why I created this item. It's actually to make you aware that I give you extra information all the time in the slides. Just check the slides a little bit and you will find more and more, right? It's more like watching Lord of the Rings several times. You always find some details, you know? It's kind of nice. I like Lord of the Rings. Yeah. Cool. I love this question. Let's go to question number 4. Because many times, well, and students all the time have problems with the question. I've been intending to change the question a little bit because probably and the issue is the question is not the students, right? When it's a repeated problem, first, the question is the problem, not the student. But let me go there. Let's go to question number 4. Oh, well, write your answer here. First. Question number 4. Let me read it aloud, just in case you cannot see it there, just for the sake of the recording. So the question number 4 says, I explained in class that simulations are good for learning complicated topics in statistics. Of course, we use simulations all the time. I also mentioned that simulations help to explain the concept of data uppercase versus data lowercase. Explain the concept of data uppercase and data lowercase using the example of tossing a coin. When we simulate one data set using the Bernoulli distribution. Is this data set data uppercase or is it data lowercase? So let me explain it here. And actually, you can use the example of a dice. Sometimes the dice is better because that was one of the examples that I gave you in one of the lectures. And I should change it for the dice instead of a coin because the coin example is boring. But so the idea of this item is to make you think about the difference between data uppercase and data lowercase. Remember that data uppercase is all the values in the universe. Remember that all these values, all these parameters that we study will have a distribution in the universe. But we don't know that distribution. We are only attempting to estimate one single value with our data set, one possible value out of infinite number of possible values in nature, right? The Bernoulli distribution is one possible model that will tell you how the data is generated. So in this example, the Bernoulli distribution is our data uppercase. Is how the data is produced, right? The Bernoulli distribution, the Poisson distribution, the Gaussian distribution, by itself are models, and they describe how the data is produced. They are our data generating process. It's also called data uppercase, right? However, when you simulate data from the Bernoulli distribution, like I do from the normal distribution, and you get one data set, only one, that one data set is data uppercase. It was already generated by the probability distribution or probability function of the Bernoulli distribution. So, in every time you generate data, you will get a different combination of values all the time, right? Similar to the example that I just gave you. If I go to our studio right now here, and of course I generate, let me just delete this. This question. If I run this code once again, right? And actually, let me do it like this, it's faster, right? Every time I run the code, I get different numbers. Why? Because every set of new values that I generate, they are data lowercase. And this is similar to what we do in real life. In real life, when you go to campus and ask questions about, I don't know, how many sexual partners have you had in your life, right? People will give you different numbers every single time you go, right? Every single time you conduct the same research project, you will get different numbers. Why? Because there is a distribution of possible values of romantic or sexual relationships for human beings. There's a distribution in nature, right? And every time you ask the question, you get a different set of numbers. But in here, we can simulate those numbers. That's why we use simulation. Because simulation helps to understand how likely is behaving our variables, right? So, in the case of the Bernoulli distribution and tossing a coin, let's come back here. In the case of a coin, if you toss the coin is your model. And every time you toss the coin, you get a different value, right? All the time. You toss the coin, get, I don't know, heads, tail, heads, tail, heads, tail. The other day you go and toss the coin again, heads, tail, heads, tail, heads, tail, all the time. It generates data. The coin is your Bernoulli distribution. The coin is your model, is the data generating process. But what you get after each trial is data lowercase. So values that are fixed, already observed, they are called data lowercase, right? They are fixed values. You cannot change it. You cannot find. Once you collected the data, that's what you got, right? Of course, you can do it again and get another set of values and another set of values, right? And all these values that you get are part of a probability model that we already established as human beings. Is the truth, right? So all these values that I generated here with a normal distribution, right? these are values that we call normally distributed because they were generated by the normal distribution. So in many models that we study here in this class, we assume that the normal distribution is the best for our model. Like for example, in regression, remember that we were studying that in regression, we assume that the conditional distribution of y given x is normally distributed, right? We assume that because we believe it's the best, right? And of course, you can change that belief all the time. But we are assuming that the normal distribution is the one that produces all the values of y given x. That's what we are assuming, right? So that's kind of the answer that I was looking for there, right? And you can also use a dice as example, right? And actually, the dice is a better example because it has more values, more possible values. So, for example, you can do sample 1 to 6, I believe. Perfect. And let me just do this. 1 second, I don't remember. That's the argument. Size. Cool. So if you have a dice, right, you will get all the time different combination of values, right? So just imagine that I'm rolling a dice. In here, what I'm doing is just sampling from 1 to 6. A dice has 6 sides, and I'm asking R to give me one number each time. So for example, I get 6 right now, right? Then I can run the model. I can run this function again. It will give me 3. Let's imagine that I throw the dice again, right? And by chance, probably I will never get 5, just by chance. But it doesn't mean that 5 is not a possible value in the data generating process. What is the data generating process? The dice. The dice generates the data. So every time I roll the dice, I will get numbers. But if I don't get 5, after 5 times of throwing these dice, it is fine. 5 is still there. It's just that by chance I didn't get it. Right? There is a process that explains that. And that process is the dice. In nature, it's the same. There is a process for everything we study. Everything that we study in psychology is part of nature. And there is a real process happening. It's just that we are limited by our senses. We cannot capture the whole thing. The only thing that we can do is to collect data and hope for being closer to the real number in nature, right? Camilo?
Yes, my question is, by collecting data using the dice, is there any way we could predict the next, like, every number that's going to come out?
If it's totally random, no. If there is a pattern where one side would be a little bit heavy, yes, you could predict something. Yeah. However, and that's a very good question, actually, Camilo. And probably, I don't know if you like playing games, right? Because games is something that actually was very helpful for statistics. For example, there is something called Monte Carlo simulation, right? Monte Carlo chain equations. And that was born because of the casinos in Monte Carlo. So it's making a reference to casinos in Monte Carlo, right? So why? Because in the long run, you could actually estimate some patterns, but you have to do it in the long run. In order to do that, we need a simulation like this one. Well, it's more complicated than this. And then you can kind of predict the next outcome. Yes, you could. But you need a simulation for that. Mm-hmm.
Yeah, I was just thinking of the roulette game, and I've seen college students try to predict the next set of numbers, or how many times it could be in the future and placing their bets higher or lower. But what I'm thinking of it as the observed data would be the lowercase data, as every time when it does come up, it was already there, but it just came up, in
Exactly, that's a
in
good
your
example.
view.
Yes, exactly like the dice, right? You turn the wheel,
Yeah.
right? You get a number, you write the number, turn the wheel, you get a number, right?
Yeah.
And that would be the lowercase. Exactly.
So then the roulette wheel is the uppercase.
That's correct.
Okay.
That's the engineering process.
Okay.
Yes, exactly. That's data uppercase. Yeah, you're right. That's a very good example too. Yes. The difference is that in statistics, we have models to understand how the data is produced. Like, for example, the data from the dice. There is something called there's something that we call the multinomial distribution, and the ordinal distribution. Those are things that we use actually in regression. Now, in question number 5, you will need to use R. So let's go here. So this is question number 5. Oh, should avoid this right here. Okay. Okay. Oh, I'm in the wrong file. Look at that. I was wondering why. System. In this question, I'm just asking you to use the function summary. So with the data sets that are already there. So the first step is just, you can copy the question as I did here, and then, of course, correct any typo, and then insert your chunk of code by clicking this little thing here, right? Or you can type it down by hand, right? That's just a shortcut if you are lazy and you don't want to type. But you could type it, right? You can type this little accent 3 times, then R, then you close the statement by typing again this little accent that I don't know how to say in English, not even in Spanish, I don't know how to say that, but it's a little thingy there. And then you're able to write your R code, right? So I'm asking you to check the function data, open parentheses. If you do that, you will see a lot of data sets, right? Some of them will be useful for this exercise. Other ones are not, right? Like I told you that be away from Titanic. It's kind of weird to say that, but it's just because the object is an array, and I haven't explained arrays, so it's not a good example for this item. So you can pick, for example, UC Berkeley admissions, for example, I believe would be good. Let me check what it has inside. No, that doesn't work. That's an array. Don't pick that one. I always use the cheeks data set, because I know it's a real data set. Oh, attitudes also. Let me see attitudes. Oh, no, don't do that. I meant to do it here. Yeah, that one works. And I don't know what it is. Let me check. What is the story behind this data? If you're curious about it, you can type question mark and the name of the data set, and ta-da, everything appears here. So it says it's a survey from employees of a large financial organization. The data gave the percent proportion of favorable responses to 7 questions in each department. Okay, yeah, it's just attitudes about the department or towards the department. So there are values for complaints, privileges, learning, races, and critical thinking, I guess, or critical, I don't know, in advance. I don't know, but it has a mean, it has a minimum value, first quantile, median, mean, third quantile, and maximum value, right? And you can delete this, and actually you should delete this if you're using Quarto. Otherwise, Quarto will try to open again this little tab, and it will crash. So just delete. Once you use data open parentheses, then delete that from the chunk of code. And what is the answer to this? Well, just run this code and tell me what is the information that you can see after running the function summary, right? And well, very clear the information that you can get from there, right? Yeah, right here. I thought I didn't include that one. Okay, so for question number 6, again, it's another exercise in R. I'm gonna just do question 6 right here. And did I copy that question? Yes. And then I'm asking you to open the data set life expectancy. Actually, the code is here. You don't have to download the data. Just copy this code. Actually, you can click here and it says copy to clipboard, right? And then you go to your R chunk, right? By clicking here. And what I'm asking you is to estimate the mean of the year 2019 by using these little pipes. So, and I'm going to copy this. Only this part is the part that I need. Then I can do something like this. Actually, right here in this line, it will work fine if you want to. In here, I do, it's 2019. Oh, and then we copy this part. Instead of this name, you just replace by 2019. And of course, you need to call the package tidyverse in this example. Okay? So if you don't do it, it will not run because this function select is part of the library or package tidyverse. Right? And then you can run the code by clicking here. And actually, yeah, that was a mistake. We do it like this. If you want the result immediately. There we go. 72.58. That's the mean of the life expectancy in year 2019. Right? That was, it's just replacing values. Many times you will have to replace values. Just take my code and replace values, right? And finally, what is the name of this probability function? Well, this probability model. What do you think? That's the only question in the part. What do you think? It's one of the guys that she mentioned. Which one? Yes, the Poisson, exactly. How do you know that?
I want to call it the right skew.
Exactly.
But that's the fancy name is the.
Exactly. That's right. It's always skewed to the right, right?
Yeah.
In this case, it's kind of weird because of the way you generate the data, but you're right. Many times it's skewed depending on how many zeros it has, or if it has less zeros, you will see more density here. But if you have more zeros, it's gonna be right here. Like in this case, I have a lot of zeros, right? But yeah, you're right. It's the Poisson distribution. That's one element that she mentioned that is good. The other one is this label right here. Number of times I say right in class for a semester, right? Number of times of something is always distributed as a Poisson distribution, right? We know that when you count things, they go from 0 to infinity in integers. And the best model for that is the Poisson distribution. Yes.
Is that also known as like a continuous distribution, or is that different?
Good question. That's controversial in statistics, because the property of being continuous is something in discussion all the time. What is really continuous, it's hard to get a really continuous distribution, but if you have more numbers here, like more observations, yes, you can call this continuous. And actually you could treat it as a continuous. However, in many books, it is thought to be classified as a discrete distribution because you have integers and counts. So for example, if your research project has only 6 people, right? 6 participants, your distribution is going to be very discrete. Your observed distribution is going to be very discrete. So it's going to be treated more as a discrete distribution in the analysis. But if you have more observations, you are totally fine treating that variable probably as a continuous in some problems. Okay. Yes, depending on the context. Yes, okay. You could do that. Well, that's a very good question. Yeah. And actually, many researchers ask the same question all the time, how to treat this type of data, right? So, yeah. So, yeah, as I said, every time you see number of times in this class, number of times something happens, it's going to be a Poisson distribution. There is another brother of the Poisson distribution, and that is, I would say, a little brother of the Poisson distribution. It's called negative binomial. That's also another possibility for counts. And if we have time, we'll explain you about it towards the end of the semester. If we have time. If not, it's fine. If you take the seminar with me, I can explain you more about it, because many of your questions in seminars are about counts or predicting yes or no, or predicting failure or success. So those are different types of models. But yeah. I'm satisfied if you can run a regression model and understand the output. I'm very good. I'm totally fine with that. And yeah, that's it. Well, we can continue actually. We have more questions here. Would you like to continue? Is this helpful?
Yes,
Okay.
helpful.
Okay, let's continue. Yeah, sure. This is your class. This is not mine. I'm doing this for you. All right. Question number 8 says, a scatter plot is useful to see possible correlations between 2 continuous variables. Is that true or false? What do you think? Do you remember what a scatter plot is?
True.
True. Yes, that's correct. That's totally correct. Yes. The number 9 says, let me explain you how you would add this to the quarto file. So you can copy the question. Quarto. Let me see here. Right? You can use 8 right here, doesn't matter. And then you write true or false, depending on what you think, right? And you do the same for all the questions. And if you want to be this bolded, you do it like this, right? The other strategy that you can follow, let me check. Oh, I didn't have that. Oh, yeah. You can see view source here. And you can also copy the whole thing here and use most of this as a template. This is the whole document written in Quarto. So you could actually copy this. I would offer the option to give you a template with the questions, but I don't have time this week to do that. So I don't want to promise something that probably cannot deliver. But you could do that, right? You will see here on the top of my files, it says code. So this is the source code. So that means that's the Quarto file that I was using for this. And actually, you can study a little bit the code if you want to do something similar to what I'm doing. Everything's open source here. So, and everything is shared with everyone. Cool. Now, the next question. Isabel conducted a study to evaluate if there was an effect of baby formula on total fat in 1-year-old babies. In this study, she had 2 groups. One group were babies fed with baby formula. The other group were breastfed babies. Which option corresponds to the best model for the best models to analyze the data? In other words, what would you use in this case? What do you think? We have two groups. Babies that were fed with formula and babies that were fed with breast milk, right?
Sorry.
Mhm. Yes,
Okay.
you both were right.
T-test, yeah.
Yes,
For
yes,
independent
that is test
samples?
for independent samples. They are independent, and that's a very important difference. What is a non-independent t-test? Well, that happens when you have, for example, time 1 and time 2, and you're evaluating the same people over time. Those are paired samples, right? You have one sample, I don't know, right now, and you do a follow-up in December, right? It's the same people. So you have paired samples. So that's what we call a t-test for paired samples. We haven't talked about that, and actually I skipped that part. I don't know why. It was there. Oh, well, so that's what we call a paired sample, right? In this case, this is not paired. They are independent. They are two different groups. One set of babies had baby formula. The other set of babies had breast milk, right? So they're different, right? And another question: what is the dependent variable here? I'm not asking that here, but just for fun. What do you think is the dependent variable? And what is the independent variable? Every answer is fine.
Dependent?
Huh?
The dependent
The dependent?
would be the fat.
Exactly. The measure of fatness. Exactly. And the independent is the group membership, right? They belong to one group or another. That's the independent variable, and the dependent variable is the percentage of fat in their bodies, right? Yes. Perfect. Now it says the p-value evaluates the magnitude of difference between two groups. Do you think that's true or false? It's 50-50. You can guess too. It's fine, no worries. It's a safe place.
False. False, because it's random.
No, because the p-value cannot measure magnitudes of difference. It's just it can't. It was not created by that. But you're right, it's false.
Okay.
Yes, it's totally right. It is false. The p-value quantifies the probability of finding an estimate by chance, of finding an estimate that is explained by chance. It doesn't say anything about the magnitude of difference between two means. The p-value is not for that, right? And actually, you will be surprised how many times some researchers will report the p-value wrongly. And they actually make inferences about the magnitude of difference based on the p-value, which is crazy. It's insane, but many people do. And actually, if you got this wrong, it will be fine because many of your faculties also got it wrong. So don't feel bad about it. Okay? Many professors will get it wrong. If I do this question, you will be surprised. Effect size. It says the effect size coins D is a standardized measure that helps to evaluate how large is the mean difference. What do you think?
True.
Exactly. One question is the opposite of the other. That's right. That's why I picked that order. In the first one, in the p-value, the way that I'm asking about the p-value is like I'm asking about the effect size. The effect size of coins D is the one that will give you the magnitude of difference between two means. It's quantifying how large is the difference between two means. The p-value cannot do that, but the coins D can. The coins D will give you how large is the difference, right? Remember when I showed you two distributions in that web page that was kind of dark with two groups and the distribution moved a little bit from one place to the other? That's the coins D, right? Now, what do you think about question number 12? Is this a positive, negative correlation, no correlation, or all the above? It is negative correlation. Yes. Why?
It's going down.
Because it's going down. Yes, exactly. Visually, when you see the line of perfect fit going down, is because it's negative. So, what does it mean? It means that when V1 increases, V3 decreases. When V1 goes up, V3 goes down, right? And there are many examples in nature of that, right? Like happiness and depression, right? If I'm very high on depression, my happiness should go down, right? What about this one? What do you think? And actually, I think I can do this. Is it a positive, negative correlation or not no correlation at all? Remember, check the labels, right? Always check the labels on a plot. Always. What do you think? Positive, right? Because that correlation between rumination and worry actually makes sense to be positive. If you ruminate more, the tendency is to be worried more, right? So of course it's positive. Yes, you're right. Always check the labels. Even if you don't understand the numbers, if you check the labels, the graph will make sense, right? And of course, you can see the trend, right? You can see a trend of dots going up, right? You can clearly see that they are kind of, you can see an imaginary line going up right here, right? Question 14 says, the p-value is the probability of seeing a difference as extreme or more extreme than the difference that you observed, assuming your data come from a process where there is in reality no difference. And I took that exactly from the book from Westwell and Henning. Is that true or false? What do you think? Kind of weird to understand, right? Totally. Too many words. No, no clue.
It's true, but I don't know.
True. That's correct. It's true. So, in simple words, what it's saying is that the p-value is the probability of finding an estimate as extreme as the one that you estimated from your data. So remember, the p-value quantifies the likelihood or the probability of finding your estimate in random data. If the p-value is very small, like 0.000001, it says that it's very unlikely that you will find that estimate in nature. So it cannot be explained by chance. Something extreme, right? I don't know if you remember when I draw, and let me just come back here. I go to the whiteboard here. Well, yes, you do it here. Let's see if it works. Remember when I draw like a distribution of values and my estimate was very far from these values, right? So this distribution right here was a distribution of null correlations. And my estimated correlation was far from the null correlations. So the idea is that the p-value is quantifying how far is this estimate that I got from the null model or the null values, right? Values that are just random, right? So that statement is trying to address that. The following statement represents the null hypothesis. Yes, true or false? What do you think? It's true. True. Yes, it is true. Why? Because I'm saying that the mean of group 1 is exactly the same as the mean of group 2. Right? That's the null hypothesis in the t-test. Right? We assume in the null model that both are the same. So we collect data to reject the null, right? Or to aiming rejecting the null. We might keep the null, and that's fine. If the evidence shows that the null is true, we should keep it, right? The mean of that the mean of group 1 and group 2 are the same, right? So yeah, that's a statement that represents a null hypothesis. Well, I already said this actually. When we perform hypothesis testing, we collect evidence to try to reject the null. And the answer is true, right? Yes, that's correct. And let's have a break. So you want a break?
Yeah.
Yes, just have a 10-minute break. Let's come back at 11:10, right? All right, let's continue. Let me just share my screen again. And I got a question about question number 3. Let me jump into question number 3 because yeah, and somebody was having a problem with this question. In this question, I'm asking you to create a correlation matrix in R. So, and actually, I explained this in the video, but it's fine. And probably in the video it was too tired. It was not a good job explaining this. So in here, what you have to do is to copy this code, right? And we go to our studio. And we'll continue with the questions. I just want to answer the question number 3. Like this, and this one is gonna be second part, right? Oh, I'm gonna add a chunk of code right here. So what I did was to copy this code from the code that I provided on this question, right? This code will open the data set in your working space. And you don't have to download any data set. Everything is in my online repository, right? So after running this code, let me come back here. I run this code. And now you should see, let me just make this bigger, PSYC object, which is the object that represents the data set, right? So you can see that it has 120 observations and 6 variables. Right? So now the data is inside R. Oh, one thing that I need to explain that I mentioned already. I mentioned already this in the video that I recorded. All the data that you open in a programming language like R or Python, that's a virtual representation of the real data. Every change you do in R to the data is not happening in the real file. That the original file is intact, it's totally intact, right? It's as it is. All the changes happen in a virtual working space, right? Because this is a very frequent question from students, like, oh, what? But if I delete one column, that means that I'm gonna delete the column in the real file? No. The original file is still there in the folder where you save it, and it's totally intact, right? You are making changes into a virtual representation of the same file. Right? I'm just verifying that. And that's also why we are able to open data from internet, right? When you open this data, because this data is located on internet, right? It's in my repository, right? You are not modifying the data in my repository. You are just getting one virtual copy of that one, right, into your working space. Right? Cool. So I asked you to do a correlation matrix. So for this exercise, you need to install the package HMISC right here. So actually, let's do it here. You can install the package by going to Packages, Install, and just type HMISC right here. I already have it, but I'm going to do it again, just in case it has been updated. I don't think so. Okay, now it's done. Now I should be able to call the package HMISC. Cool. Let's already there. I run this by pressing Control Enter or Command Enter on Mac. And then I can follow the code that I provided right here. Okay? So in here, instead of data, you are going to use the object PSYC and estimate a Pearson correlation. Do they type something wrong here? Oh, yeah. There you go. So now, there are two pieces of information. We have a matrix with correlations and a matrix with p-values. Yes, it's weird, I know. P-values should be like a table, right? But given that it's a correlation, it's a matrix of correlations, it kind of makes sense to have a matrix of p-values, right? So, for example, what do we see here? We see the correlation between great and cheerful, right? And the correlation is positive and kind of high. And it makes sense, right? If you feel great, you are also cheerful, right? So the correlation coefficient is 0.64. And that correlation is not explained by chance, according to the matrix of p-values. They decided to call it P, but it's the p-values, right? Of course, it's not obvious. There are many things that are not obvious in R. So don't feel bad if you cannot guess or you cannot understand the output sometimes. I know. It takes time to understand the logic of R. But yeah, the correlation between great and cheerful is not explained by chance. Why? Because that value is way lower than 0.005. Right? And the same happens with other correlations. However, other correlations are not like that. Like, for example, the correlation between cheerful and sad is actually explained by chance, because this number is greater than 0.05. So it is totally explained by chance. And let's see what is the value for the correlation. Cheerful and sad, the correlation is minus 0.09, almost zero. It makes sense, right? There is correlation, it's negative, but it's so tiny that, yeah, it's just explained by chance, right? According to that QI. Now interpreting the results. What it would do is to copy this. Actually, I gave you a paragraph on how you can interpret the results in question 3.2. Right? Actually, I'm not gonna write the question, but we can do it later at home. I'm gonna do. Right? And in here, you interpret the results in simple words without using R, right? You don't have to use R for this part. Just copy the paragraph. So it says the correlation between variable 1 and variable 2 was with value, but it's just a template. So instead of variable 1, you can write the correlation between, let's take an example, between great and cheerful. Yeah, why not? Great. Cheerful was 0.64. 0.64 at 1 minute. 0.64. Insert. I hate 0.64 with a p-value of, let's see, well, you can just use p lower, not uppercase, p lower than 0.001, because it's a very tiny number. It says 0 here. If you type 0, I will understand that you understand. It's fine. It's a very big number. This means that when variable, this means that when cheerful increases, Oh, sorry, greatness. I want to call it greatness, I guess. Or great. With great. With great increases, cheerful also increases. Whereas the correlation between variable 3 and variable 4 was negative. So it's just an example, right? So what you have to do is to replace here the names and just use the same wording that I'm using, right? That's the idea. I'm just giving you a template on how you can report correlations. I'm going to do the same for regression probably later in another assignment. So you would see a piece of a narrative that you can use on how to report these statistics, because that's another question that is very frequent. Or how can I say, yes, frequent or normal in students. How do I report this? Right? What is the right wording? So I'm going to be adding that later. I don't know if this answers the question. Yeah? Cool. Okay, cool. And actually, let's render this and see how it looks like. It'll take some time. Still thinking. My computer is not very fast, but here it is. Right? So it says first part, question 1, question 2, question 3, question 4, question 5, right? Question 6. And the second part that I was explaining was question number 3. And you can see here the correlation matrix and the matrix of p-values, right? And you don't have to copy and paste it. Just generate that, right? Cool. Let's come back to the questions. Oh, this one. Constant variance is an assumption in the classical regression model. Is that true? We just saw it the last.
No, we on 16.
Oh, sorry.
We on 16. We not finished 16.
Oh, we already answered that one. When we perform hypothesis testing, we collect evidence to try to reject a null. Yes, I think
True?
Yeah.
it's true. Yes. Yes. And what about number 17? Given that the test and regression are practically the same, what do you think? They are the same, and you will see it later.
True.
Yes, it is true. Yes, one of the strong assumptions of the classical regression model is that the variance at each level, the variance of each conditional distribution at each level of x is constant or the same. Right? It's the same. That's the assumption. Right? And what about this one, 18? When conducting a t-test, you could correct your test if the variances are not equal between groups. Can we do that? It's fine, you can say no, yes, it's fine.
False.
It's false?
Weak. Can we
No,
correct
it's not
it?
false, it's true.
True.
You could correct the t-test. There's a correction for that. The first implementation of t-test is named student t. But if you correct your t-test, it's going to be called the Welch t-test, right? And actually in R, I explain you that there's an argument that says variance not equal. You can change it to true or false, depending on what you are assuming, right? So yes, the answer is yes. You can correct. You are able to correct your t-test if the variances are not the same, right? If the model doesn't hold the assumption. What type of model am I running here? In this piece of code right here. What do you think?
Classical regression model?
Yes, exactly. Classical regression model. Why? Because we are using the function linear model, LM. Yeah. Classical regression model. You are correct. Now, in question number 20, it says, according to the famous and ugly rule of thumb, a p-value less than 0.05 is considered enough evidence to claim that any estimate cannot be explained by chance alone. Is that true or false? It's true. Yes, the answer is true. Why? Because that's the rule of thumb that we follow in science. If a value is less than 0.05, we consider that enough evidence to say, oh, my estimate is not explained by chance, right? It's not explained by random data. It's not explained by a random effect or something like that, or something random in nature. It really happens, right? But I told you that that value shouldn't be considered like cast in stone, right? It's not like that. Even though many people make you believe that it should be a very strict rule, it is not. It depends on the topic on many things. For example, if you get a p-value that is 0.06, this is still meaningful, right? Or 0.07, it's still meaningful, right? It's just the 0.5 was accepted because 95% of chance of finding 5% of chance of finding that estimate among random data sounded like a good number. That's why. Right? Of course, the lower the number is better, right? That means that your estimate is more extreme. It's way far from random data. So that's fine. That's something that we always want in statistics, well, especially in research, when you really like a topic. Or you believe you're right. Well, you might be wrong. And that's the idea of science. To find out if you are right or wrong. And number 21, it says, before conducting a test, we should check the assumption of equality of variance by performing the Leibniz test. What do you think? It is true. Why? Because every single model will have assumptions. All the models, all probability models will have assumptions. And we need to test those assumptions first. We need to test if our model holds the assumption. If not, we need to find another model, right? So that's why we always test the assumptions all the time. Not only to test in regression, in ANOVA, in logistic regression, in SEM, or many other models, we always test our assumptions. Or the ones that we can. There are assumptions that we cannot test because those assumptions are more about the data generating process and very abstract, hard to quantify. So I must say that some assumptions are not testable, but most of them are. And yeah, cool. Questions so far? I'm not going to explain this part because it was already recorded. So I don't know. Unless you want me to explain something in detail, of course, we can see it together. Right? Questions? Yeah, here. Is it perfect? Perfect. Yeah. And you saw the logic of Quarto, right? Like, and when it's text, don't use a chunk of code, right? When it's just English, and don't do that. What is this? Dates. Okay, go ahead. Don't do that, right? The chunk of code is only for our. Is that question on that? Sorry, I'm saying that if I could go over 2.1, okay, let's check that. The concept is for rumination. Okay. For this question, 2.1, and actually this is a good time to explain this problem. And this is something that I also explained in the practice number 2. right? Probably you are working on that one as well. Why we are creating, in this question, why are we creating a composite score or total score? Well, the thing is that in psychology, given that we work with latent variables, we work with abstract concepts that we assume we can actually measure, right? One of the ways to have a real indicator of those abstract concepts that we call latent variables is by adding items together, adding questions together. What we do in psychology, for example, many times, is to create a Likert scale, right? And Likert scales, remember, are more about like something. I can do it here. So in Likert scales, you will see answers, well, response options from 1 to 5, right? So for example, if I ask you how depressed, no, actually, I can use that from the practice. Let me just go to the practice first. Let's go here. So what we do is to ask questions about how you feel, for example, right? And people answer these questions from 1 to 5, where 1 is, I don't know, I don't feel it, and 5 means I feel it too much, right? What we do is to take each of these boxes, these are items, observed items in your survey, and we take the data set and we add these items together. Just assume just an addition, a normal addition that you would do, a regular addition in arithmetics, right? And then you get a total score for each individual in the data set, right? That final score for each data set, that total score, is the one that we use for data analysis. And you might be thinking, and why we don't use each individual item? I mean, those are valid answers. Yes, they are. Well, the problem is that we need to find a data reduction strategy. Imagine that your depression, imagine that your depression scale has 50 questions. You cannot analyze 50 questions individually. Well, you could, but you will not find a good pattern, in the sense that it's just so difficult to analyze 50 items. At the end of the day, what you want to do is a theoretical inference and a statistical inference about depression, not about each individual item. So one way in psychology that we kind of want to be closer to the latent variable is by adding these items together and get a total score. And you will do it in the seminars. That's what you have to do. Not only in seminars, in research in general, in psychology like that, right? When you are working with self-reported instruments, right? Okay, good. So in that exercise, what I'm asking you to do, and sorry if I over-explain this again and again, you might be bored about it, but I just want this to be clear. So in this exercise, what we are doing is taking this data, rumination, and creating a total score for depression and a total score for rumination. So each individual in the data set, and I don't know if I added an example here. Let me see. Oh, no, it's not here. Oh, I probably deleted the part when I was editing this. Well, each individual in the data set will have a total score. And actually, let's do it right now. This is question number 5. No, number 6, I believe. I need a piece of chunk from here, right? And then let me copy this. 1 second. For this exercise, you have to call the package tidyverse or just use this package dplyr. Dplyr is inside tidyverse. So if you run this code, even by copying this, it should be fine. It will run fine. So let's imagine I do this. Just as a common rule in the R world in Python, every time you use a package, it should be at the beginning, right? All the time, at the beginning of your chunk, or at the beginning of your assignment, right, of your file. You can create a first chunk at the very beginning, right here, right? And this one is gonna be only for libraries that you use, right? So if you do this, you are making sure that you already have the libraries that you need to solve the whole homework. Like for example, tidyverse and HMISC, right? So you are sure that every single time you run this file, you are calling the right packages at the beginning. That's one way to do it. Or you can do it in each chunk, right? Just to communicate to you in the future that we're using that package. All right. So I took this code. Let me just read in the data. Let me just move this probably because it looks fine. When I'm reading the data. And remember, we are using this argument because this data has missing data, right? So in this data, every value that is 99 is going to be considered missing. But it could be any number. I just decided that was the number for this data. Right? And in here, if I follow this code, look at that. I created these two scores. If you don't believe me, because, I mean, why you should believe what I say? You should never do that. I mean, that's part of science. You never believe me. No, for real, it's not a joke. I mean, if you don't believe me, that's fine, that's good. You have to be critical about it. So in here, you can go to data rooming, click here, and look at that. The new scores are here at the end. So every new column is going to be at the end of your data set, right? So we have a total score for depression and a total score for rumination. Nice. Now, in that exercise, I'm asking you to create a scatter plot of depression by rumination. There are several ways to do it. Actually, one of you sent a very smart quote, probably, I don't know where she or he found it, but it was a very clever one. Or, oh, sorry, let me just add a new chunk of code. So in here, you can use data rooming, $, actually tries to guess, to depression, data rooming, $, and then this one should be rumination. And look at that, that creates this beautiful plot where you can see, well, kind of see it's a positive correlation, we already know that, right? And it says estimate the Pearson correlation. So let's do that. Now we can also estimate the Pearson correlation. Let me add this little chunk of code. We are going to use. You can just copy this part here. And use. And I'm going to use pairwise complete ops. Complete ops, what's the option? Oh, yeah. And that's the correlation. Now, notice what I did here. I'm using this argument called use. Why? Because I have missing values. If you have missing values, you cannot estimate something with nothing. If there is a cell that is empty, of course the software will choke. It would say, no, I cannot compute this. So what I'm saying is only use people who have scores on both variables, right? So if for some reason somebody did something like this, let me show you. Sorry about that, it's just, here it is. If we go here, let me just go to, so let's imagine you have variable 1 here, and variable 2 here. Right? So let's imagine you have a score right here, score right here, score right here, score right here, empty or N8 in R to N8, and then 45 here. So if I do a correlation between these two, I cannot do it because I'm missing information here. So by adding this argument pairwise complete observations, R will ignore this guy here. So it will totally ignore in the computation process. And it's gonna use only the observations that have scores on both variables, right? Remember, each row is an individual, right? Each row is one participant. So yeah, this participant has 2 scores, in variable 1 and variable 2, and this other participant 2. So he or she is gonna be part of the correlation estimation. The other guy, well, he or she is gonna be ignored because he or she forgot to answer one question. Oh, sorry about that person. That's what happens. So if you were trying to answer this question and you couldn't compute the correlation, it was because of that. That's a very common mistake. And why is that happening? Well, because many softwares will do that by default. Some softwares that we use for teaching and will kind of try to predict that you have an ace or something like that, and you don't realize that you have to do that. So it's the curse and also the bliss of having automatic things in some softwares, right? You don't think about those things, but you should, right? That's why I like R. It will make you think about many things. All right, hopefully that answers the question about Saria. I don't know if you have any other question about that one. I guess it was fine. Okay, you didn't answer, but I guess it was fine. And let me see what's in the seat. I don't have time for more. Okay, well, let's stop here. Hopefully this was useful. And remember, if you have questions, send me as many questions as you need. And this can be also a good video where you can see what is the logic behind the findings. Soon you will see assignment number 2. Now we went a little bit faster. So soon you will be assignment number 2. And it's the same logic. You will see exactly the same logic, right? You copy and paste the questions, or use the source code that is in the right corner on the file. You can copy it, right? Or just do it in Word. If you don't want to mess with Word, it's fine. Remember, this is just extra. I will give you extra points every time you do it in Word, but it doesn't mean you have to. So thank you so much for being here, and see you the next week. Have a wonderful week. Huh?